Now we've looked at power functions and we've looked at algebraic rational functions, but let's look at the end behavior of a function that's a little more complicated, like 3x minus 2 over the square root of 4x squared plus 5. The process for calculating the limit at infinity is the same. We're going to look at the denominator and pick the highest degree term. Now be careful, this is not the highest degree term. 4x squared is inside of the square root, so really the highest degree term is 2 times the absolute value of x. So when we go through and divide every term in our function, we're not going to divide by x squared, we're going to divide by the absolute value of x. I'm going to write this like this. Now I can't squeeze the absolute value into that radical without changing it a little bit. So let's put the denominator on pause. We can clean up the numerator. If we're assuming x is going to positive infinity, then absolute value of x is just equal to x. So then our expression becomes 3x over x minus 2 over x in the numerator. In the denominator, we have the square root of 4x squared plus 5 over x. And for x to go into that radical, we're going to write it as the square root of x squared. So then in the denominator, we will have 4x squared divided by x squared plus 5 divided by x squared, all inside of that square root. And on top, we'll have 3 minus 2 over x. And as x goes to positive infinity, that function that we have, anything with x in the denominator is going to go to 0. Anything without an x in the denominator is going to be like a constant. So we have 3 minus 2 over x. Our denominator looks like the square root of 4 plus 5 over x squared. So this term goes to 0. This term goes to 0. We're left with 3 over square root of 4, or 3 over 2. And I'm going to let you finish that one on your own. If you want to do the limit as x goes to negative infinity, you'll repeat the argument. The only difference would come in right here. So if you're doing the limit where x goes to negative infinity, then the absolute value of x is going to look like negative x. So you would just make that replacement and then continue on. Now that we know how to use limits at infinity to calculate the end behavior of a graph, we can basically sketch a function without using something like Desmos or a graphing utility. It's a long process though, so hang on. Step 1, determine the domain of the function. You always want to make sure that you're graphing a function over its domain. Most of the functions that we work with aren't going to have domain issues except for where a denominator is equal to 0 or where you have square root with a potential negative inside. So first thing, check the domain of the function. Second thing, find your intercepts. Third thing, you're going to find the end behavior, going the left and the right, checking to see if you have a horizontal asymptote. Fourth step, determine if you have any vertical asymptote. That's when you're dividing by 0. That causes the vertical asymptotes. And then step 5, you'll calculate your first derivative to find the extrema, max and min. And step 6, you'll calculate your second derivative. That way you can make sure that you're drawing the concavity correctly. So let's take a shot at it. Now, as the function is written, you might first think, let's multiply it out. But we have tools for taking derivatives of the function exactly as it is now, so I will encourage you to leave it. Step 1, the domain. It's all real numbers. So this function will go from negative infinity to positive infinity. X can be any number you want. There is no x value that breaks that function. Step 2. What was step 2? Locate the x and y intercepts. So the x-intercept, that's when y is equal to 0. So we'll set our function equal to 0 and solve. If this function is equal to 0, then it's either the x minus 1 factor that made that 0, or it was the x plus 2 factor that made it 0. So the x-intercepts will occur at x equals positive 1 or at x equals negative 2. We know those points have a corresponding point of y equals 0, so we know that our x-intercepts are the points 1, 0 and negative 2, 0. The y-intercept is going to be when x equals 0, so we just plug x equals 0 into our function. So we get, 0 minus 1 squared times 0 plus 2. That gives us 1 times 2, or 2. So our y-intercept happens at x equals 0, y equals 2. Step 3 of our function was find the end behavior. If x goes to positive infinity, we're looking at a polynomial. So if the degree is even, our end behavior opens in the same direction. If it's an odd, then it's going to open in opposite directions. So if we multiply this out, that first factor is going to have an x squared term. Multiply it to the second factor, we will end up with the leading term, the highest degree, highest exponent on x is a 3. So we know we're working with an odd degree. So our end behavior is going opposite, and there's no negatives here to make that highest degree term negative, so we know that as x goes to positive infinity, our function is approaching positive infinity. As x goes to negative infinity, our function is approaching negative infinity. Think of those polynomial graphs we talked about earlier. Step 4 was determine if there's any vertical asymptotes. Our function doesn't have a denominator, so it's not possible for it to have any vertical asymptotes. Right? We're never dividing by 0 here. Step 5 and 6 is derivatives. So let's go ahead and do those. So step 5, is the first derivative. We need the power product rule here. So the derivative of that first term uses the chain rule. And then multiply that by the second term plus that first term times the derivative of the second term. And we can clean that up. So we've got 2x minus 2 times x plus 2 plus x minus 1 squared. Oh, I should have left that 2 factored out. If I left this as 2 times x minus 1, then I can see that both my terms have that x minus 1 factor, leaving behind 2 times x plus 2 plus 1 factor of x minus 1. We can clean this up. Oops, that shouldn't have a square outside of it. It was just one of those. So we've got 3x plus 3. If we set this equal to 0, we can find our critical points. So we have a critical point at x equals positive 1 and a critical point at x equals negative 1. And then lastly, we need to find our second derivative. So we're going to take the derivative of our first derivative, and you can use any version of what we have down here at the bottom of our screen. I'm going to take the derivative of this last step. It's the cleanest version there. So if I do the second derivative as step 6, then I'm taking the derivative of x minus 1 times 3x plus 3. That needs a product rule. The derivative of our first term is just 1 times that second term plus the derivative of the second term times the first term. It's going to leave us with 3 times x minus 1. Distribute that over. We get 3x plus 3 plus 3x minus 3, or which leaves us at 6x. This function is equal to 0 only when x is equal to 0. So at x equals 0, our concavity changes. To the left of 0, our second derivative is 6 times x. To the left of 0, x is negative, so we have concave down. To the right of 0, x is positive, so 6 times x would be positive, so we have concave up. Using all of this information we can now sketch our function. So I'm going to squeeze that into this top corner up here. So the first thing I'm going to do is put my intercepts on the graph. So I have x equals positive 1. Let's try and color code this. Put the x-intercepts in blue. So I have one x-intercept here, another x-intercept here. We can do a y-intercept in yellow. That'll be about right here. We're going to use our end behavior last. So we do know that as x gets crazy large, our function is going up to positive infinity and negative infinity when we're going to x goes to negative infinity. So we know we're going to end up with a positive infinity here and a negative infinity here. But we have to figure out what goes in between, and that's where the derivatives come into play. So we know that our function has 2 critical points, one at x equals positive 1, one at x equals negative 1. Well, at x equals positive 1, we are on one of the x-intercepts. So this is either a max or a min. And then at x equals negative 1, we are about right here. If we plug x equals negative 1 into our function, we get 2 squared, which is 4. We get 4. So that y-intercept was at 2. This other point is going to be up here at 4. And then we have our concavity from step 6. It says from negative infinity all the way up to 0, our graph is concave down. Using that, we can connect our y-intercept to this point we drew from our critical point, back down to our x-intercept, and then we can continue downward because of the end behavior of our graph. We know that the concavity after 0 is concave up, so that y-intercept might be our inflection point, and then we are going to connect it to our critical point slash x-intercept point, and then turn it around to go back up to positive infinity because we determined the end behavior should match that. And that's pretty much the sketch of our graph, connecting our dots. So if we didn't have a graphing utility like Desmos or our cell phones or any kind of graphing calculator, we would be able to come up with the general shape of a function just by using these 6 steps. A rational function is a little bit more work to sketch the graph, and that's because we don't get to skip step 4 like we did in the last example. So let's go ahead and give this one a shot. All right, so step 1 for the domain, 1 minus x squared. this can give us a 0, but other than the 0 in the denominator, this function is going to go from negative infinity to positive infinity. So at x equals 1, we do have a removable discontinuity there, but it otherwise is continuous. Step 2 are x-intercepts. Those happen when y is equal to 0. The only way to get a function that's a rational function equal to 0 is to set the numerator equal to 0. So if we set x squared equal to 0, we can see that x has to equal 0. So we have an x-intercept at 0, 0. And then for our y-intercepts, we're going to plug in x equals 0. In this case, that would give us 0 divided by 1, or 0. This shows us that our x and y-intercept is the same exact point. Step 3. Step 3 was finding the end behavior. So we're going to do the limit as x goes to positive infinity. And for sake of space, I'm just going to rewrite that as x goes to positive infinity. Our function, well, we need to use that trick that we use. Find the highest degree term, divide every term by it. So looking at our denominator, the highest degree term is x squared. So we'll divide every term by x squared. The numerator becomes 1. The denominator becomes 1 over x squared minus 1. As we let x go to infinity, that 1 over x squared term goes to 0. We get negative 1. As x goes to negative infinity, we use that same version of the function, the 1 over x squared minus 1. And although x is going to negative infinity, we're squaring x inside of the function, so that term goes to 0 as well, meaning the function is approaching negative 1. So we have a horizontal asymptote at the line y equals negative 1. Step 4 was check for any vertical asymptotes. That comes from the denominator equal to 0. So if we set 1 minus x squared equal to 0, we could see that we will have a horizontal asymptote at plus and minus 1. So the two vertical lines, x equals positive 1, x equals negative 1. I feel like I might have said horizontal asymptote at some point. I apologize. Step 4 should all be vertical asymptotes. For the sake of time and space, for step 5, where we find the crit points, instead of going through the derivative and calculating them, I'm going to give the critical points to you. There's one at negative 1. There's also one at 0. There's one at positive 1. So we find 3 critical points, and if you have forgotten already, those come from setting the first derivative equal to 0, or finding where the first derivative does not exist, meaning the denominator equal to 0. So we find 3 critical points that we need to test using the first derivative. These 3 critical points break our number line, the x number line, into 4 separate intervals. We need to test each one. So if we test to the left of negative 1, we find that our function is decreasing, so the derivative is negative. If we test between negative 1 and 0, we see that the function is still decreasing. So x equals negative 1 is not actually a max or a min. Then if we test between 0 and 1, we find that our derivative is positive, so our function is increasing. And then the same thing is true to the right of positive 1. Function is increasing, derivative is positive. So we can see that we have a minimum at x equals 0, but we have some fake out critical points at positive and negative 1. Step 6 is where we test concavity. Again, instead of calculating the derivative with you, since that's something that we learned a long time ago, I'm going to kind of spoil it for you. When you take your second derivative and set it equal to 0, or take your second derivative and find where it does not exist, you can find possible inflection points. So if we take our second derivative, set it equal to 0, we find our inflection points occur at -1 and +1. So we found those in the critical point process, but we weren't able to classify them as a max and min, and that's because they're actually inflection points. To the left of -1, our second derivative is negative, so we're concave down. In between -1 and +1, our second derivative is positive, so we're concave up. And to the right of -1, we again have a second derivative that's negative, concave down, so we have two inflection points. All of this together will allow us to graph our function. So let's do it. So let's draw our x and y axes first. Try not to make a mess out of it. We'll start off by putting our intercepts on the graph. So I'll try and color coordinate these again. X-intercept / y-intercept at the same point, so I'm just going to plot that right there at the origin. We know that we have a horizontal asymptote at y equals -1, so let's call this y equals -1, and we'll just put a dashed line. Well, there goes color coordinating. Whatever, we can handle it. So our horizontal asymptote occurs at y equals -1. We have a vertical asymptote at x equals -1 and x equals +1. So let's draw those in. Vertical asymptote, vertical asymptote. We know our function won't cross over those. We found a minimum at 0, so this point that we have at the origin, that is a minimum for our function. And then we found inflection points at -1 and +1. Now we should graph those, so we need to plug -1 and +1 into our function. F at -1 would look like 1 over 1 minus 1. Ooh, infinity. So that's our vertical asymptote. F at +1, well, that gives us the exact same thing. And we could have seen that coming because we found vertical asymptotes at those values. If there weren't vertical asymptotes at those inflection points, we would plot the inflection points on our graph, but that's not happening this time. So at this point, we have all the information that we can get about our function, and we're just going to do our best to graph what we can. We know to the left of our vertical asymptote at -1, the function is concave down, and that we have a horizontal asymptote at y equals -1. So our graph is probably going to look like this over here. Notice that as x goes to -infinity, we approach the horizontal asymptote, and as x approaches -1, we get close to the vertical asymptote, going all the way down. Between our vertical asymptotes, our function is concave up, and it passes through that minimum. It actually looks like a parabola. And then to the right of our vertical asymptote at x equals 1, we kind of have the same thing as what we had on the left side of the graph. As x gets very large, we're approaching the horizontal asymptote. As x gets close to 1, we approach the vertical asymptote. I know that we went through each of these sketching a function problems quickly. You do know how to do every single one of these steps prior to this section, so that's why I went through it fast. If any one of these steps feel like they're unfamiliar, Go back and revisit the earlier sections of the textbook. That way you can start to review and strengthen your understanding of those concepts, and then move forward. So that's it for this section. If you are reading the book, which I hope you are, you'll notice that there's some material that we're not covering, and it basically boils down to anything that has to do with transcendental functions. We don't cover that in our Calc 1 class. We do late transcendentals, which means you learn that in Calc 2. So anything that involves e to the x power, log x, or ln x, we don't do that in this semester at all. In fact, we don't do calculus on inverse functions either. So you can skip both of those things throughout Calc 1 at Merced College. And then also, I'm skipping the examples that graph a function with an oblique asymptote and a function with a cusp, but I would encourage you to try them on your own if you have enough time. That's it for section 4.7. I'm going to try and work on more videos so that we can try and catch up, because all this stuff is causing us to fall behind. But hopefully you're reading the book and it's making sense to you. All right, see you next time.